Yeah, hello. I think I don't have to introduce myself. I've been standing here quite a few times. I hope this is one of the last talks about how we did it, because now it's just a common feature, and Steve has given a presentation about the current client status and how it works, and the KSMBD does it, and this is pretty much a wrap-up that I've already given in some other conferences at FOSDEM. About how we did it, what the technical challenges were. Steve's talk just 5 minutes ago was more about a little demonstration and the end user perceived value of this. And this is more about the technical background, what challenges we had to face. And yeah, essentially kind of a wrap up of the at least 10 years of talking about SMB3 Unix extensions. Back then when they were still called SMB2 Unix extensions. Okay, why? I mean, we've talked about this during this conference. And yesterday, when preparing this talk, again a bit, just going over the slides again, I remembered OpenBSD on their website, they were asking the question, why do we ship cryptography? Because we can. That was back in times when OpenBSD still was under US export restrictions on cryptography, and they were proud to be shipped from Canada, where you could actually export DES and Kerberos and all that stuff. And they said, okay, why do we ship cryptography? Because we can. Why do we want to do this? Essentially, we want to provide an offering to make file sharing more secure by default. The main downside of NFS for me is that it's used usually in a very insecure way, just with no file security whatsoever. Because Kerberos is hard to set up in the NFS world. We've had customer engagements where we couldn't find out the bugs in the Kerberized Linux client. I mean, this might have been all fixed now, but it's just cumbersome and hard, and SMB3 11 is secure by default, and Daniel has given a great talk about how to make this just as usable as NFS with all sys. And yeah, you have a spectrum of really easy to use, unsecure, and really safe. Everybody has to authenticate properly with Kerberos and so on. It's just an offering by the Samba-Team and the Linux community for file sharing to become more secure in the Unix world than it usually is being utilized in NFS. What do we want to do? Again, I told Ralph maybe it would have been better to let me talk before Steve, but this wasn't really possible. We want to make the perceived experience of a Unix home directory, and maybe at some point even a diskless Unix or Linux workstation possible over SMB. We want to make it a competitor, and so we have to use the extensibility of SMB, and I will show you one or two Wireshark traces, how we use this. We want to use the extensibility of SMB to really add these POSIX features. There's a few aspects to it: file name handling, case-sensitive file names. POSIX is case-sensitive, which means that you can have test.txt in lowercase, test.txt in uppercase, in all combinations, and you can make up the math how many versions of test.txt you can have in your file system, in a single directory. How did we do this file name handling? How do we control this? We make use of the extensibility of the SMB3 protocol. Essentially, what you can do when you open a file over POSIX, over SMB, the call as such is extensible. The protocol element to open a file can be extended with contexts, essentially with extended attributes, and within these POSIX extensions, we are telling the file server, hey, for this open call, please do all POSIX stuff that you want or that you can. Steve has shown that we are able to use, to transmit POSIX metadata. What is POSIX metadata? If you look at the statsys call, and this is much too small, man to stat. This is the POSIX call to retrieve information from a file, and somewhere we should have a, it's not in here.
It might be in main inode.
I just wanted the structure where we get the information. So what you do when you want to display metadata, and I'm at this bullet POSIX metadata here, POSIX has some different notion of what a file metadata is. It has an owner in a special format. Windows has an owner, but the format is different. It has an inode number. Windows has something similar, slightly different. It has permissions. It has all sorts. It has a link count, something that Windows doesn't have. So this stat call that I just put up the man page for here is a way for an application to ask the file system, hey, get me all this metadata, and we need to provide this metadata via POSIX. How did we do this? We did this with a so-called new information class. And this is another aspect of the SMB protocol, that you can just extend numeric fields. So when you ask for metadata for a file over SMB, the client asked for so-called info levels, and that's at least a 16-bit field, out of which maybe 20 or 25 or so numbers are taken. We just reserved one more number with Microsoft where we put all our information. So what we do when we issue this stat call, we ask for file information in our version, extending the SMB3 protocol, and we get all stuff that we want within the protocol with a separate call, with a separate so-called info level that a file server that does not implement this just ignores, gives an error or something, invalid level or something, but any file server which implements this will give us the right information. So this is extensibility of the SMB protocol really used. We start to have a specification for this, thanks to Ralph. And we are still in discussion with Tom Telby sitting here, what a real specification and documentation and all the legalese around must, should, may, and whatever should not actually means.
All of section 3. It's like processing.
Yeah, so, and we have to get used to all these technicalities that are required to make this a proper spec in a Windows or in an SMB protocol specification language, to make it really usable for others as well. Not just the Samba-Team, not just the KSMBD people, not just whatever. Somebody who can essentially look at our code. There are a lot of people who are just for legal reasons not allowed to look at our code, but they still need to be able to implement this properly. And so this is not enough. You can, of course, look at our code, what we actually did, but yeah, we need to make this proper. So what problems did we have to solve? First, of course, these little stat information, but that was relatively minor. Windows works very well with files and directories. SMB works very well with files and directories. But POSIX goes a bit beyond that. And there you have these 7 file types. The first one is a regular file, what you also have in Windows. Second one, SIFDIR, is a directory. We all know this. But then there's these 5 others. Typical Linux, Unix, file types, special files, block device characters. This is giving you access to your hard drive. This is giving you access to your keyboard, to whatever, to your null device. And then there's interpros inter-process communication endpoints represented inside the file system. And this is the FIFO and the socket. What does it mean? Normal inter-process communication in the internet is I open a TCP socket on an IP address, on a port, somebody can connect. These two here are essentially the same concept, where I can open a Unix domain socket or a FIFO, offer services there, represented in the file system. And if we want to make this smooth across the network, we need to represent these when exporting and importing this via SMB. How did we do that? We have to step back a bit. What is Samba's role? A block and character device presents the hardware that is attached to the computer where this file system is sitting to user space. What does that mean? This computer here, it has a hard drive, not really a rotating Rust, but a little whatever NVMe, M2 or whatever. It has a hard drive, and the operating system running locally on this machine that I can touch is represented with a so-called block device, dev SDA. So if I go in as a process and open dev SDA, I get access to the hard drive blocks in my machine here. We have to think a bit about what this should mean when we do this over the network. When we export this /dev, this local file that represents access to my local hard drive, when we export this over SMB or over NFS or so, we have two choices. The first would be that we give the remote client access to my local hard drive. Doesn't really make sense, and we don't do that, but this would be one choice. The other one is that we just let the client see this as a local device, and if dev SDA is exported in some way with all its metadata, it represents the local device on the client that mounts this remote file system. And this is what we do. So if you just export dev now, which just takes garbage, this could mean just if somebody writes there, this is sent over the network and thrown away on the server side. Just doesn't really make sense. But but still, we have to represent these files in a way that the Linux client using POSIX extensions can actually figure out, yes, this is dev SDA. Similar for FIFOs and sockets. And this is an interesting one. Because what we could do is somebody on the server side opens a Unix domain socket. Like your SSH agent, your GSS proxy. You export that file. This socket for the SSH agent or for X11 whatever display is exported and is visible on the client. What could that mean if I open that file? It could mean that over the network I connect to the SSH agent on the server. And this is exactly what Windows does on the IPC $share with named pipes. This is exactly what is happening in the Windows world when somebody creates a named pipe on the IPC $share, client connects there. It is connecting a client process to a server process for just data transfer, essentially like a TCP socket. I can only imagine that these named pipes were from the world before TCP, from NetBEUI or whatever. You had a transport, and you just reuse this for inter-process communication. That's my interpretation of things. We could do this, but we don't. We do the same thing as with devices like SDA or DevNow. So a client can run the SSH agent. The SSH agent on a client machine needs to present some services inside the home directory of a user, but it runs on the client. So, but the files, when you mount /home, actually reside on the server side, on the server. But still, it's local inter-process communication. And yeah, home DS over SMB must present these file hosted sockets for local IPC on the client. But we need to represent them somehow. The hottest one is the last one, symlinks. There's been a lot of talks, and Jeremy Allison has given very vocal talks about that symlinks essentially need to die. And the world would be so much better off if we didn't have symlinks. And it's the worst invention by BSD that they could have given us. But they are there, and they are very handy. People use them. But even the Rust community had their symlink race problems. I mean, Rust is the programming language that claims to be secure, but in their tooling they had symlink races. And just Google for symlink races, you will find thousands on thousands of CVEs and so. How do we deal with all of these? As I said, NTF or SMB is extensible. We used that. We extended the protocol with our own little calls. And not only SMB is extensible, NTFS is also extensible. I said a few slides back that NTFS is very good at files and directories. NTFS is also good at so-called repass points. What is a repass point? And until I kind of implemented this, it really was a gray area, very opaque to me. I heard and I read that NTFS repass points are just a file with an exatter, but this doesn't really catch it. What is a repass point? Wikipedia says repass points provide a way to extend the NTFS file system. A repass point contains a repass tag and some arbitrary data. And it also says this is interpreted by a file system filter driver. That's Wikipedia. What I found out when researching about repass points, the thing that happens is essentially Windows opens a hook, Windows file system, Windows NTFS opens a hook for applications to intercept the open call. Tom?
I'm disagreeing with you. Go ahead.
It intercepts, it opens a hook to intercept the open call. So, a Windows application comes along, opens a file, and you can preload a DLL into your Windows kernel or whatever, a shared library, that attaches to this hook, maybe something similar to BPF, what we have in Linux these days. And you attach to this hook at the end of the open call, and if you open a file that has this special extended attribute that we are talking about, if it is tagged as a repass point, the open call in Windows goes and sees, okay, hey, we have a file with a repass tag, with a repass tag number. I mean, essentially, I believe, 32-bit number. Then, if this file is about to be opened, it walks the list of preloaded DLLs, whether any of these DLLs has registered for this hook, for this repass tag. And if then it finds one, so we open a file with a repass tag 1, somebody has pre-registered its DLL, registered, okay, we have repass tag 1, then a special callback is called, do something with this. Evaluate a symlink, or fetch a file from tape, fetch whatever, do something, do a virus check on this or whatever. If you want to open a file with a repass tag, number 1, and nobody has loaded this DLL before, responsible for repass tag 1. You get this very weird status IO repass tag not handled error call. And so that's all repass tags are. A special extended attribute that is evaluated when NTFS opens a file. And we can utilize this. Martin? I can repeat the question, if it's not too long.
Who can set the tags?
Anybody can set the tags. So you open a file, the question was who can set the tags? I open a file with a open as repass tag flag somewhere, and then there's special FS controls where I can say, okay, essentially set this xattr, a special version which is exactly called set repass tag, and I set this repass tag, and then at the next open time, Windows will try to interpret this.
Any application can set the reparse tag, but only privileged applications can install a filter driver that will interpret them.
Tom's comment was that anybody can set the repass tag, but installing this DLL interpreting these, the filter driver, that's privileged, obviously. I mean, not everybody should be able to extend the Windows kernel or the file system or whatever. So, Martin.
So who does the filter driver run as? The person accessing the file? The user who installs the filter driver?
It depends on the filter driver's code. It basically...
The question was, who does this callback run as? Tom's answer was, it depends.
I think it's usually the kernel.
We have another comment, it's usually the kernel.
Usually, but it can impersonate, it can do all
Yeah.
sorts.
It depends. Microsoft has defined a few dozen repass tags. For some of them, they also documented the format of the extended attributes attached to these. For most of them, they say, okay, they are not meaningful on the wire, which essentially means we don't document them. Okay. We have a subsystem in Windows that is facing the same problems. I was talking about how to represent symlinks, how to represent special files, how to represent sockets, and so on. Windows has a still running NFS server, and there's the same problem. This NFS server runs on NTFS. And what does the NFS server do if somebody does a make FIFO, or a make node, or a symlink or so? So, and they used, they export normal NTFS, and they have a repass tag defined. It's IO repass tag NFS, some magic value, and they define subtypes there. This is documented in the Microsoft documentation. They define a symlink on their own. And interestingly, if you go to the Explorer window, if you create a block device over NFS and you look at that with the Windows Explorer, all you see that this is a symlink. Because the Windows Explorer as an application isn't really aware of all these types of repass tags that can be there. It just says, okay, it's a symlink. It's an L for symlink. Okay. So, what operations do we need to support? We just discussed that it doesn't really make sense to open a socket to open a block device over the network. That doesn't make sense. It will be relevant when we list directories. Somebody needs to be able, or the client needs to be able to identify our symlinks, our FIFOs, our sockets over the network. If we ask with the stat information that I just showed, if we ask the file server, hey, give me the stat information for a block device, we need all the metadata for that block device. And listing directories was a very hot topic in the last few whatever SDCs when Steve and others were sitting together in a room. Why? Because when you list a directory, it can be very inefficient. Because when you do a man read dir, this is the way a Linux application asks for directory entries, and this dir end essentially only has the name. I think this is not really in the standard, where it says, okay, I'm listing a directory, and I already in this call give you a type. This is not in the standard. The standard only says, I get you the name. But when you list a directory on your command line in Linux, it already tells you, either with color or with a little letter at the very left column, yes, this is a symlink, this is a block device. So the standard, and this is what NFS did in the initial release, when listing a directory, only gives you the name. But the GUI and the command line UI in Linux needs the type. And so what ls-l has to do, the command on Linux, it has to ask for each and every file, it has to ask, hey, I have SDA, what is this? A round trip. Hey, I have symlink, what is this? Yes, it's a symlink, another round trip. And this is why NFS invented readdir plus, already by standard returning all the types, so that ls-l gets faster. And we do the same. We do the same thing. We don't want the client, the ls-l, we don't want to force the ls-l to go back for each and every name to ask for the POSIX information in the same way that I described with yet another info level. And so we added another info level to the Windows version of readdir plus, so that the client can, at the first run, already ask for all the information that it wants for ls-l. That's the same info level for the stat call that I described. It's essentially the same data fields. And so we have readdir plus, we invented our own info level for that, so that we don't have all these these round trips. And so last year's talks, we had a slide on WSL versus repass. We solved that. And that's really going into details. Essentially, there's two versions, or there's more than one version to represent all the NFS information. Windows NFS server is one, WSL version 1 is another one. For symlinks, we have even more. And so essentially what we did in the last year, we settled on a solution that makes this really fast with all the POSIX information. And talk to me later if you really want the fine details. So listing directories should be fast now. Symlinks. The things that Jeremy wants to get rid of. So, NFS server, the NFS server in Windows gives us a way to represent, in normal Windows NTFS style, represent block devices, sockets, FIFOs, character devices, and so on. With symlinks, we have three choices. And we have the NFS spec symlink from the NFS server. We also have WSL symlinks. There was a version 1 of WSL, Windows Subsystem for Linux, running on NTFS locally. They had the same problem. They had to represent symlinks, and they invented their own way of doing symlinks. But then, not many people actively use them. NTFS itself does have symlinks. Easy to use, must be a bit configured, but these symlinks that NTFS has is pretty interesting for us. Why? And I want to show you a network trace. So what is a symlink? A symlink is, okay, I have I want to point a place in the file system to a completely different directory, different file, and so on. Very useful in Linux. And the problem is when I open a path over a network, what happens? We have many choices. Over SMB, I open a file, and somewhere in that path that I give to the SMB server, there's a symlink. What we are doing in Samba, typically, up to now, is if the symlink is sitting on the server side, we just follow that on the server side. And that is really opening the door for many security vulnerabilities. And we want to get rid of this. So what happens is the client gives us a long path with many components. Somewhere in the middle, there's a symlink. We don't want to do anything with that server side. What's our choice? We figure out, okay, there's a symlink. We don't want to have to deal with that. We tell the client an error message. So now the client only knows, hey, there's a symlink. What the client then, in theory, has to do is step by step see, do a stat, do a read link, and whatever. Not so with the native NTFS reparse symlink. And this is what I want to show you. Can you read this? And this is really great. This is I think it's
pretty small actually.
okay, better?
Yeah.
Okay, so I want to open a file. And I told you that this file has many components, many path components. A/dir/c/x.txt. And somewhere in the middle, there's a symlink on the server side. And this is completely standard SMB behavior. No POSIX extensions, no nothing. This works on NTFS with Windows. The nice thing is, the server told us, hey, there is a symlink somewhere in this path. And if this was all the information that's there, the client would have to ask, is A a symlink, is dir a symlink, is C a symlink, and whatever. Where does it point? Windows is smart enough to actually extend this stopped on symlink error message with a lot of metadata. The first thing is unparsed data links. What does this mean? This means we have a length of 16. This is all counted in UCS2, or rather 2 bytes per character in whatever encoding. So we have to count from the back. We have to count 8 letters from the back, because this is, the server is telling us, I could not look at 16 bytes from what you sent to me, which translates into 8 letters. 1, 2, 3, 4, 5, 6, 7, 8. So here it stopped at this backslash. At the second last backslash, it had to stop. And so this means that this one here was a symlink. This dir was a symlink, actually. And what it also gives us, the error message, where does it point? It points to B. Okay, I can't really scroll this up. But essentially, with the native Windows way to handle symlinks, we just in one round trip get all the information that we need to essentially replace this dir component with B. And this is all we want to do with symlinks, to just then in a second request, in next request, go and try the target of the symlink. We want to resolve the symlink client side, and this is why we settled essentially on handling symlinks, not the NFS way, but the native Windows way. Oops. Okay, and this is our behavior now. when a client negotiates POSIX extensions, this is also the behavior if you say follow symlink equal no. So we have a setting in Samba that says, okay, follow symlink equal yes, that's our default, because that's what we've been always doing, and which causes a lot of trouble with security vulnerabilities, because somebody could point to /etc shadow, and together with other security vulnerabilities, we would open etc shadow, essentially violating the promise that we only share /data or the share root or whatever. And this is why we want to get rid of following symlinks on server side. And right now, if you negotiate POSIX extensions, a proper Linux client with POSIX mounts, we never do that anymore. We don't ever follow symlink server side anymore. Instead, we return this stopped on symlink so that the client has to deal with all of that. You can also just configure your Samba server without POSIX extensions, that in that you just say follow symlink equals no, and we do the same thing even for native Windows clients, and they should be able to deal with it as well. Although then you have to take what does it actually mean to have a symlink pointing at /etc? So following symlink's client side might have a completely different meaning than following symlink server side. So you have to really adjust your notion of symlinks a bit, because they are, with follow symlink equals no or POSIX extensions, they interpret it somewhere else. So it doesn't really make sense to point a symlink from A to B or to /something, because /something doesn't make sense on the client. But it's still, we got rid of the problem. Let the client take care of it. But you had a question? Okay.
I was just smirking at the comment.
Okay. Okay. What do we do if we want to create one of these things? So what I was talking about is Samba behavior when it finds existing of these special files. It finds existing symlinks, it finds existing sockets, it finds existing character devices. What do we do when a client comes in and wants to create one of these? We mount /home, and the client needs to create a socket for the SSH agent running locally. What do we do? We could, so Martin asked, how does a client do that? You create a file, and we represent these things as repass points, and the client will do exactly the same. The client creates a file. It will give us the extended attribute, hey, this is a socket repass point for the SSH agent. And what we could do on server side is we could, in theory, create a socket server side. This would get us into all sorts of trouble, however. Permission. And it would open up, with symlinks, it would open up races again that we just got rid of. So if on a SMB client somebody said link ln-s, create a symlink to etc, we don't want to see this as a symlink server side. So we just create a file, we set a special attribute, we set a extended attribute saying, okay, this is the repass point, and this is the metadata for the repass point, and let the client deal with it. So for the SMB client, we just give the illusion that it can create a repass point, it can create a symlink, that the client will see as a symlink. However, on the server side, it will just be a plain zero-sized file that has special extended attributes. And you could, in a second step, then go and say, okay, I want to turn this into real symlinks and so on, but we don't do that yet. So from a client's perspective, it should be fully coherent. You can create symlinks, you can create sockets, you can create block devices, and so on. On the server side, this will just be plain files with special extended attributes. Okay, last slide, I believe. Okay, no, not almost last slide. This is what we discussed yesterday already in Daniel's talk. NFS by default is insecure, which is very handy, in particular for compute jobs, for HPC, for whatever, long-running jobs where somebody fires up 1,000 whatever Linux clients transcoding a video or transcoding pictures or doing some AI training or something. You really don't want to deal with authentication there because it's hard. You just want to fire up your compute jobs, and some student, some scientists just submits a compute job and it should just run on 1,000 machines, 10,000, 100,000 machines. And for this, you have to think very hard about, okay, a scientist submit a job. If you really now want to be sure that this job can access resources on a file server under this scientist's privileges, permissions, authentication, that's really a hard problem to solve. Kerberos has a lot of solutions for this, and this is what Daniel presented as essentially. What we could have done is the SMB protocol has an extension where a machine, like one of these 1,000 compute farm clients, can be given the privilege to impersonate users when accessing shares. That's this remoted identity tree connect. So the SMB protocol has an element where when connecting to a share, the client can request, okay, I want to connect this share, but under this identity, using these privileges. Standard SMB protocol element that, of course, needs special coding on both client and both server side, and that needs to be very carefully done. Is this client machine actually entitled to do so? Entitled to say, okay, I'm root on this share. Please let me in as root. I'm Tom on this share. Please let me in as Tom. And yes, we could have done this. And before I heard Daniel, this was actually the plan. But with GSS proxy and all this Kerberos delegation and constraint delegation business, essentially this is not required anymore. We can do that now. So with this constraint delegation concept, what you can do is on your KDC in your Active Directory, essentially you can give client machines the privilege to impersonate users, and the software on the client machines to do this already exists now. And so this problem is essentially solved. And so we can now really take care of all these long-running compute jobs where the client machine will be able to impersonate in an audited and secure fashion, impersonate the scientists submitting his batch job that is running for a week or 2 or a month. And yeah, that's all done now. And so I think we have a pretty compelling story now to offer a secure way to share files using SMB and make it as usable as NFS in the Linux world. We have a few open things, few open questions. When do we want to default to follow symlink equals no? I mean, with POSIX extensions, the client is fully aware that we don't do the old Samba behavior of following symlink server side. But on a completely different note, we want to get rid of following symlink server side. And so at some point, this needs to be mature enough so that we just default to not follow symlink server side. Different node. We have that code for POSIX special files. And then the big topic, ACLs. We don't cover that yet at all as part of this effort. I mean, of course, you can do your ACL business over SMB. And none of this is restricted in any manner. But I think to get a complete story, the complete story right for the average home directory or the average project directory, we somehow need to enable setfACL and getfACL as people are used on Linux, on local Linux. And we haven't really decided yet how that is to be done best. because then you get into much more severe trouble with your ID mapping, with your actual semantics on what POSIX or what ACL semantics do we use? Do we reuse the SMB ACLs? Do we, whatever, extend something with NFS ACLs, with NFS v4 ACLs, or whatever? Once we have established this as a good thing, I think we have to have more slides, more talks about how do we represent ACLs so that the average Linux admin is happy with what he is used to, or she is used to. But they, exactly. That's my talk.